Hey gang, and welcome back to another worksheet solutions walkthrough for the worksheet, reaction practice of ketones and aldehydes, part 1, getting them down. Okay gang, so if you're here, I just want to say, take a deep breath. I know that there are a ton of reactions for ketones and aldehydes, and you know, keeping them straight is one thing, solving them involving problems is a whole bunch, a whole other thing. No worries, we have some practice here. You're clearly watching this video for some answers. So what we're gonna do is we're gonna go top to bottom on the worksheet. I'm gonna show you how to go, how I attack these problems, how I arrive at the answers that you've already hopefully seen, and hopefully at the end, they make a little bit more sense. So let's get after it. Okay gang, in problem 1, we have a whopping 14 complete the reaction questions. I included this many because I wanted to kind of get you practicing and recognizing acetals and forming amines, forming enamines, all that good stuff. I just wanted to give you a hefty bit of practice. So what we're going to do is there's going to be, I'll have 4 kind of shots of this segment. So this is the first 4 of 14, and then we'll do 4, 4, 3, and 3. So if we take a look right here, so again, this is all about ketones and aldehydes, and we do have a whole host of new reactions that we just learned. So the question is, what do we have going on in this first one? Well, I hope you're seeing obviously that we do have a ketone, and I hopefully that you saw that this is a diol, right? We have 2 alcohols. We're in an acidic environment, and I even put minus H2O just to be very explicit, right? That might not always be there, but I'm, for the purpose of this worksheet, put it on there. This is acetal formation, and you can see that it's acetal formation where we have our alcohols packaged in one. We have a diol packaged, so 2 alcohols packaged in one structure. So whenever you do this, basically, you're going to have this point attached to these new oxygens right there. So you can almost think this is going to happen, this dot being this right there. So we have as a product, because this is the only chemistry, the only step in this reaction, we have that dot carbon, and you can draw a line and know it's going to go to an oxygen, on both sides. And the thing is that these 2 oxygens just happen to be connected together by 2 atoms. So 1 and then 2 right there. So that is the acetal. That is our product for the first reaction. We move on to 2. Okay, so now we're getting some multi-steps involved. So you can see we already have an acetal here, right? We have 1 carbon right here attached to an O-ethyl on both sides right there. So we do have an acetal to begin with. So this first step, since we're adding water back in, remember how we talked about, the nucleophiles we work with for acetal formation are not that great. So to overcome that, right, we had to protonate the carbonyl carbon. We also had to overcome the bad entropy and drive water off, right? We put it back in, it reverses the whole shebang. So in this first step right here, all we're doing is unraveling that acetal and recovering the carbonyl it came from. So that is after step 1. Now, I hope what you're seeing in steps 2 and 3, that's just a reduction of a carbonyl. That is H- coming in and attacking. However, when we attack that carbonyl though, and then we protonate it to form an alcohol, we are going to form stereocenters. So don't forget, your day ones. Don't forget your, organic principles and everything you've learned along the way. We will form a stereocenter at this position, right? We will form, if you even wanted to think of it, you could think to yourself, okay, I know I'm going to recover my carbonyl, and I'm going to reduce it to an alcohol. Then you could look at this and say to yourself, oh man, okay, I am attached to 4 different things. So this is a stereocenter. So attack happens equally on top and on bottom. I make an alcohol that is both wedge and dash in equal amounts. And because this is the only stereocenter in our molecule that was created by the attack, we can then write plus an enantiomer. So that's where that came from on the solution sheet, okay? All right, so I'm going to erase this because I'm going to need this space right here. So in this problem right here, we are given the product, we're given the reagents, and we need to come up with the reactants, okay? So I hope what you're seeing is this is H+, and it's saying minus H2O. So basically this is saying we're in an acidic environment, and we created what I hope you recognize as an imine, right? Because that nitrogen-carbon double bond. So how do we, we have to come up with a carbonyl and an amine, A-M-I-N-E, right? So remember, we know if we cut that bond, this dotted carbon was a carbonyl. So the carbonyl was just cyclohexane, pentanone, right? A 5-carbon cyclic structure with a C double bond O. And if I want to map the dot carbon on both sides, it's right there, okay? It's a kind of a short stuff pentagon I drew. Now, the amine. Remember, with imine formation, we either use ammonia, NH3, or a primary amine. So I hope what you're seeing is, here's the primary piece, it's an ethyl piece. So all we need is this, right? You attach the carbon piece, you know you're still gonna have a lone pair, right? And you just fill in the hydrogens you would have had. So in a primary amine, you have 2 hydrogens, okay? Alrighty. And last but not least, for the first part of this monster first problem, we have this carbonyl. Again, very similar to kind of with the first one, but I hope what you're seeing is, yep, acidic environment, we're gonna lose water, we're gonna be doing one of these formation mechanisms, but this is a secondary amine. And remember, while with imines, we need primary and or ammonia, with secondary, because we only have the 1 hydrogen to deprotonate, remember, we form enamines. Okay, and remember, we try to form that E double bond. We try to form a double bond that minimizes the sterics of our reaction. So what I want to show you is what we'll draw first. We know we're going to have a nitrogen up here, and I drew that kind of, well, let me draw this a little bit better over here. We know we're going to have this right here. Okay, that's better. Now the question is, which side does the double bond go on? Now this is interesting. This is a ring. So we have the option of putting this blue double bond right there, or what I'll draw is the black one. Only one's going to stay. If we have the black one, I hope what you can see is that will lock this methyl group in place, okay? That will cause steric strain right there, okay? So if we're going to lock in one side, let's lock in the side that doesn't even have a group. I know this is a little bit different than, it's because there's no concept of the double bond like being able to flip E or Z as we have in a straight line structure. So on a ring, you want to lock in the less substantially big side rather. So it's this right here that we want to go with, okay? On a straight line structure, we have the ability to make the double bond here and then flip that methyl group down. We don't have that luxury on a ring. That's why the double bond goes to the left. That's the enamine you form. That is part 1, my friends. Let's move on to part 2. Okay, gang, rolling on into part 2, we see in our first problem, we're going to see a primary alcohol and our first step of PCC, and that's nothing for us. We know that's going to take our primary alcohol and oxidize it to an aldehyde, but no further than that, right? So we will have, if I'll do some work over here, you'll see, I'm just going to redraw the aldehyde like this, and now, so hopefully in 2, so you might see the Wolff-Kishner written in 2 steps. One where it's very explicit that it's happening, you know, in acidic, and you have the hydrazine, the H2NNH2, or the the N2H4. But it's very common. Don't be surprised if you see it written like this, where you have it all in one line with the the base, where it basically looks like a basic environment. So we basically got we took an alcohol, oxidized it to an aldehyde, a carbonyl, only to just wipe it away, right? We know the Wolff-Kishner just wipes it away. So all we're left with is this structure right there, okay? 1, 2, 3, 4, 5 carbons, just to make sure we didn't lose any. Okay, so that's the first problem. Second problem, so hopefully, okay, we have an aldehyde, benzaldehyde to be exact, if we want to flex our common naming knowledge, and we have the cyanohydrin formation reagents, right? This is an easy one. But be careful, stereochemistry, right? And I know that's really lame, but stereochemistry, it never goes away, gang. So we know that we're going to have the nitrile attack, or sorry, this, CN minus, cyanide attack. This will boot up, and then we'll protonate this up. So at first, right, feel free, and that's exactly what I did. You didn't see how I had to edit the answer key after the fact. We will have this, and remember, there's a hydrogen there. 4 different things, right? We know we're attacking an sp2 trigonal planar carbon, so this gives us a racemic mixture. The only stereochemistry we have in this molecule was created from the attack. So make sure you reflect that this is a chiral center. However you want to draw it, I'll choose to show this, and then you write plus an enantiomer. And just so you know, I could have absolutely made the line to the CN a straight line. Doesn't matter because I showed one stereo isomer and then I wrote plus an enantiomer, so there's going to be an R and an S representative there, okay? Now, here, so I hope what you're seeing is I see a carbonyl, and remember, this right here, when you see, oh, and I dropped a letter, I'm sorry, gang. It needs to be PPH3. Oh, and I always do this. I'm so sorry. I'm sorry if this needs to be adjusted on the worksheet. That's triphenylphosphine, right? So that's a P and then phenyl, PH, not a phosphorus hydrogen with a subscript 3. So when you see this, I want you to, in your mind, whether it's your teacher says illid or yillid, whatever, but this is I'm gonna say yillid, and we have a carbonyl. This is screaming Wittig reaction, okay? And remember, we will always make a Z double bond, or cis if it's, one group on each side of the double bond, but you have to make sure your yillid is not attached to a conjugated system, right? Because if so, then we do the E double bond, remember. So here, just a plain old, straightforward, going to actually make a cis double bond here, in Z, but cis more specifically. So we have 1, 2, 3 carbons here, 1, 2, 3. So to really easily link them together, what I'm going to even do, so you can see that this carbon is this one over here. 1, 2, 3. I'll even asterisk this one right here, because you have to make sure, since we, our yillid is not off of a conjugated system, we're going to make a Z, or more specifically here, cis double bond, because we only have an R group on each side. So it's a Z, more specifically cis. That's our Wittig reaction here. Okay, now down here, it looks like, and I need to specify this down here, we have another Wittig reaction, but this time we need to come up with the yillid as well as the carbonyl. Okay, so one thing we need to check, because I'm seeing a benzene ring, and that could potentially affect whether we get a Z or an E double bond, or here, more specifically cis or trans. But I think what you can see is this double bond, this is a cis or Z double bond, okay? So in picking right here, the choice of our yillid will actually affect what kind of double bond we get. So because this is cis, Z, right, that means our yillid was not off of a conjugated system. So follow me here. This section, right, has to be the yillid, because if the yillid is on the other side, that will actually change the product we would get, okay? So these two carbons have to be the yillid. You can draw it like we had it up here, where the phosphorus has a positive and the carbon has a negative, or you can draw it like this. You can draw a double bond. So you see there's 2 carbons here, 1 and 2. This is that carbon right here. This is the other one, okay? So here, let me do this a little bit better. We could have this, and in which case the charges go away, or if you want it represented above, this is more familiar to me actually. These are equivalent is what I'm trying to say. And this is the carbonyl on the other side. Again, it's benzaldehyde. And again, this has to be the way it is, because if we switch the roles, if this was the carbonyl and that was a negative carbanion attached to phosphorus, triphenylphosphine, we would actually get an E double bond, right? Because we're off of a conjugated system, the yillid, that is. Okay, gang, that's part 2. Let's do part 3. Okay, gang, rolling into part 3. Right up here, I hope what you're seeing is carbonyl, and yes, we have another secondary amine. We see acidic environment. This is screaming enamine formation, okay? Now remember, we're going to have this nitrogen and its 2 groups, that's the 2 ethyls attached right here on the nitrogen. Let me clean this up because that was kind of ugly. Now the question is, right, where do we form that E double bond, right? We obviously want to try and minimize sterics if possible. Well, what I want to draw your attention to is we can't even eliminate, there's no hydrogen on this carbon over here, because that's where that double bond comes from in the mechanism. Remember, we take off an alpha proton, right? One position away from this carbonyl is the alpha position. We have to deprotonate here. We form a double bond. These electrons kick up back onto the nitrogen. So we actually don't even have an option here. We have to make the double bond over here. And in doing so, we flip that methyl group down. We form the E double bond. And that is, so you can see, that's the first carbon, and then we just have, you know, something like that. So, oh my goodness. Nope. Didn't put the double bond in the right place. There we go. I was thinking that looked weird. And then of course you have the T-butyl group, the rest of it over here. So because there's no proton available here to rip off, you know, you're forced into this choice, and remember, make that E double bond. E because, right, we know this is how that double bond goes in terms of priority. That is not on the same side, that's E. Okay, and it helps minimize sterics. Okay, so moving on to here. So again, we have another Wittig reaction, right? And a real quick scan, we don't see any type of yelid off of the conjugated system, so we're not going to worry about the E double bond. We're going to make Z or cis, right? So that's what we're gunning for, Z or cis, if cis is available. So we know this carbon's going to be part of the double bond. We know this carbon's going to be a part of the double bond. And in fact, what you're going to see is Z and cis won't apply here, and luckily this is a really simple Wittig reaction. So I would just draw the 6-membered ring exactly the same. You know you're going to have a double bond right away that's connecting this piece to now this carbon right here. So I'll go ahead and dot that. And because there's no difference in priority on this side versus this side, it doesn't matter how you attach the group, whether it goes this way or this way. So I'm going to feel free. I'm just going to attach it over here. So you can see there's my 1 carbon, then there's my 5-membered ring. So it doesn't matter if you draw that to the left or to the right, because there's no concept actually of cis or Z here, for that matter. Okay, last but not least, we have this carbonyl in the benzylic position, and all we have is a reduction going on, right? This is simple, but I wanted to make sure I threw a deuterium problem in there, because that never goes away too, just like stereochemistry. Stereochemistry a little bit more important, but people love to slip deuterium in every now and then. So remember, we're going to be attacking with D-, and then we're getting our source of, you know, proton, if you will. I'm not saying this is an acidic environment at all. I'm just saying after we attack, we have an O- here, and we grab an H to quench that negative charge from ethanol. So we're going to have a deuterium attached to the carbonyl carbon, whereas we'll have a hydrogen on the carbonyl oxygen after the fact. It won't be a carbonyl though. So remember, deuterium will attack the trigonal planar carbon from, yes, both sides, because this is a problem we have to worry about stereochemistry. So after the fact, we have our product right here. We have what I'll choose to draw as a wedged OH. I will draw a dashed deuterium, and actually let me draw this a little bit. I'll draw this methyl group still on the plane of the page. I'll draw a deuterium over here. And because, yes, this is the only stereocenter we created, or a stereocenter in the molecule, and we created it from an attack of a trigonal planar carbon that happened in equal amounts, we can then write plus enantiomer. This is a racemic mixture. You know, the mixture itself won't rotate the plane of polarized light, all that good stuff. Okay, so that was part 3. Let's finish off this monstrous first problem with part 4. Okay, gang, to finish out problem 1, we have 3 more lovely complete the reaction problems. So, on this first problem right here, we see we have, again, cyclohexanone. And what we can see up here is thioacetal formation. Again, if you use different reagents for thioacetal formation in your class, just, you know, ignore whatever I'm using. I'm using what was in my textbook, what I'm most familiar with. So we see we have this sulfur, this dithio, and then we have zinc chloride and some acid. So what we will do is we will form a thioacetal, right, on this carbon here. So what can be tricky here is actually getting all the carbons involved. So you see we have this carbon will be bonded to both of these sulfurs, right? So the first thing I would do, draw 2 lines to sulfur like this. Now just think about how many carbons are between those sulfurs on this structure right here. 1, 2, 3, right there. Okay, so 1, 2, 3. Whoops. Nope, that was how many lines I was drawing, which is exactly what I did when I first made this problem. 1, 2, 3. 3 carbons in between. So actually, you end up having another 6-membered ring, right? So 1, 2, 3, 4, 5, 6. Okay, and that's that problem. Okay, so now moving on to the second problem, I hope what you're seeing is this is a Baeyer-Villiger oxidation, okay? Because, and again, if you use a different peroxy acid or a more generic one, that's, you know, do you, this is a peroxy acid, right? So remember, when we do Bare Villigers, we see we have a carbonyl, and we know we're going to get an ester out of this, right? And remember, the only trick someone can throw at you is using or tossing in some migratory aptitude. So what we need to do is we need to compare our two alpha positions right here, okay? The alpha position being one carbon away from our carbonyl carbon. So this is secondary. This is tertiary. And remember, we can go up to tertiary. We can't work with quaternary, but tertiary beats out secondary. So we're going to insert this oxygen right, pretty much in between here. We're not breaking the bond, right? And oxygen is going to go in between here. So we're actually going to grow from a 5-membered ring to a 6-membered ring. So I'm just going to go ahead and draw that. So what once was 1, 2, 3, 4, and 5. Now we're going to have, 1, 2, 3, 4, and 5. Obviously that oxygen is in there, but don't forget we have a methyl group on 2. Okay? So the trick there was just making sure you don't lose any carbons, you don't lose where the methyl group is supposed to go, and you evaluate the migratory aptitude. Alright, so last but not least, we have this right down here, and what I would encourage you to do, and I did this kind of on purpose, because not everyone hands you things in a nice way in OCHEM, but draw these aldehydes out, I always prefer to see them the way they're meant to be seen, Because that's what they are, the CHO, they're just aldehydes. Okay, so in this first step, I hope what you're seeing is acid and this, and since no one's said excess, assume one equivalent. And because we're symmetrical, I'm going to erase this up here. I just assume we're going to protect one of these things. Doesn't matter which one you work with, but I would say after one, you're going to have an acetal on one carbonyl, where one carbonyl was, and you're going to have the other just left over. Okay? Now we see butyl lithium. Okay, so in that second step, so this is 1, moving on into 2, right, we're going to have butyl lithium, which is just like a Grignard, right, in terms of strength and whatnot, attacking the aldehyde. Okay? So what you can think of, we still have this right here. Now all we have is OH, and I'm just going to write Bu for butane, butyl, whatever. So that's what we have, and then this third step, I even jumped the gun. Third step is a workup with deuterium, okay? So in step 3, we're going to quench this up here. Now one thing I skipped over, and what this will also do is this will undo the acetal, and if you work out the mechanism, no deuterium shows up over here, because all we get left over with is just the OH, the oxygen from this right there, okay? You can work it out, you can trust me on that. So, one thing I forgot to reflect, because this does look like our product, but remember, when we attack this carbon right here, yes, we are going to create a stereocenter, right? We are attached to 4 different things. So, this is going to be a wedge, and you will have to write plus enantiomer, okay? So all this problem was, just to recap it real quick, is protecting, because we have one equivalent, one of these groups, and it doesn't matter which one because we are symmetrical here. So we protected one of the carbonyls, we turned it into an acetal, right? Leaving us with one aldehyde that's eligible for attack from a good nucleophile, and that's what we got with butyl lithium, right? Just a Bu minus, you can think of it just like that. It will attack a trigonal planar carbon. We then are attached to 4 different things because there's a hydrogen, there's this thing over here, there's what will become an alcohol, and then the butyl chain over there. And then we have the workup with D3O+, which does more than one thing. It quenches the negative charge, but it also unravels the acetal, leaving no trace of deuterium here, but leaving a trace of deuterium right there. And we had to reflect it. We created a stereocenter, and since it's the only stereocenter in our molecule, and the one we created in equal amounts, we wrote plus enantiomer as well. Whew, gang, problem 1 was a beast. We have 2 more. I think you're going to see that we'll get through them much more quickly than these. So stick with me, 2 more, and we'll finish out this walkthrough. Okay, gang, I even suspect that you saw this problem and you knew exactly what was going on. So we take a look, we have, our 2 reactions. I labeled them 1 and 2. So you can see it's acetal formation, right? And actually here it's hemiacetal formation because we're only going to, in both cases we only showed the addition of 1 alcohol to the carbonyl. And we see one is faster and one is slower, and I think it's very obvious why. So here, right, we have our nucleophile packaged in with the carbonyl we're working with. Here they are separate molecules. So if you want to think about it in terms of entropy, right, lovely delta S. Delta S is back, right? So we have two reactants going to one product. And up here we have one reactant going to one product. So if you want to think about this, the change in entropy for reaction 1, the delta S sub 1, if you will, right? You know, there's, you know, we could argue that it's roughly 0. Maybe it's not, but you know, 1 to 1, same amount of disorder on both sides. Here you can see the system. We have less things bumping around. We have fewer, you know, things after the fact crashing into the walls, crashing into each other. Our system gets more ordered. So if you want to think about it, the delta S sub 2, you know, I don't know what it is, but I think it's roughly equivalent to a frowny face. So the point here is that the change in entropy is not a bad thing. Down here, we can qualitatively assume it's not good. So that's why this is a more favorable, faster reaction. It's because you're not changing the entropy in an unfavorable way. Down here, you are. Okay, gang, that's 2. Kept it real nice and sweet. Let's end on problem 3. Okay, gang, last but not least, problem 3, hitting you with a mechanism on the outro. Okay, so you can see up here, we have this lovely structure, we have H2SO4, and then all of a sudden 2 rings appear out of nowhere, right? A 5-membered ring and a 6-membered ring. So for a hot second, we have a meltdown, but then we realize we're smart, we know organic chemistry, and we can figure this out. So when you see this, right, it doesn't look like a lot of information, but this is actually everything, right? This tells us we have an acidic environment on our hands. We have H+ floating around everywhere, okay? So I hope one thing you're picking up on is you see that we have a carbonyl right here, and we no longer have that up here, and we have some extra bonds. So what I'd hope you think, like something that will spring to your mind, is we're in an acidic environment. We know carbonyl oxygens get protonated easily. That's what we've been doing ever since we came into contact with aldehydes and ketones in jOeCHEM 2. So let's protonate the carbonyl carbon and see where it takes us, okay? So first off the bat, and to save myself some space, what I'm gonna do is I'm gonna draw H2SO4 up here. I'm gonna have that oxygen, grab H+, this just to save me redrawing this gigantic structure one time, okay? So we have that. We have the nitrogen, this down here. So all that did was protonate this, right? But now we know that that makes this carbonyl carbon that much more reactive, right? And you can see that we clearly have a connection between this carbon and this being, you know, assuming that's the carbonyl carbon, right? So where is that carbon coming from? We do see that it is, you know, if I number it in here, 1, 2, 3, 4, 5, and 6, it's coming from carbon 4 in the ring, and if I were to number 1, 2, 3, 4, 5, 6, you can see that if we can make this bond happen, that can work. And that's kind of the key. I know we haven't used carbons to attack carbonyl carbons yet so much in this fashion, but that's part of this mechanism, right? It's kind of just seeing if you can figure that out. And really, you know, protonating the carbonyl oxygen, seeing that you've made that carbonyl more reactive, and then saying, I'm going to, in a Markovnikov addition type fashion, have this carbon attack this carbon right here. So after the fact, right, all we're really doing is creating this bond right there. So I'm just gonna go about my business very similarly. The structure didn't change all that much, but you'll see that that opened up the gate for the rest of this reaction. So, right, we have 1, 2, 1, 2, and then now we have this ring with, we still have this methyl group up here, right? This is now just an OH, okay? And remember, this carbon said, okay, I'm gonna take charge and I'm taking both of the electrons in this bond. That left this carbon right here that I'm going to asterisk, you know, down the river without a paddle, SOL. Now it's a carbocation, okay? So we have a carbocation right here. It's tertiary. We're not going to rearrange it. However, I think maybe you can now see what's going to happen next, okay? We've handled this part. Now you can see that we've made a bond from the benzene ring to what is now carbon 3, right? 1, 2, 3. And we've definitely done an EAS, a generic EAS reaction where benzene just grabbed a carbocation because EAS, electrophilic aromatic substitution, putting positive stuff on benzene, right? So all we're gonna do, it's this carbon right here that's gonna be calling the shots, but if you can already see the makings of 1, 2, 3, 4, 5. This is how we're gonna form our 5-membered ring. So this carbon will take the double bond, we will attach right there. I'm gonna draw my line over here, I'm gonna draw my work down here. So I don't have this double bond for the moment, okay? And this carbon took the electron, so it's carbon number 2 that has a it's carbocation. We'll have to regain our aromaticity, but that won't be a problem. So I know I'm gonna have a pentagon off of this now. And if I even want a number 1, 2, 3, 4, and 5, I know 5 has a methyl group. And I know that 5 and 4 are a part of a 6-membered ring. So I might even draw the methyl group a little bit more like this to support drawing this, and I kind of drew it funky, but I think you can see now everyone is connected in the right way. It's a little tilted, and I'll make sure it's better in the next structure. Okay? So all we need to do now is, there's a hydrogen here, just like any other EAS mechanism, we need to deprotonate this and regain aromaticity, and the conjugate base of the acid we used at first will help us pick that off. We'll swing these electrons down, regain our aromaticity, and in doing so, let me try and draw this a little bit better now. Oh boy, nope, I don't think so. Let me see. Then we have nitrogen, this. I think that's it. Okay, so the point being, gang, let me make sure that's actually right. Okay, looks right. Okay, so the thing is that we protonate the carbonyl oxygen. We've been doing that. That's nothing new. That makes this carbonyl carbon more reactive. We form a 6-membered ring. We see that this nucleophilic double bond could help us out. We attack using the double bond. That gives us the ring, that gives us the alcohol, but it also creates a carbocation there, super advantageous to set up for this generic EAS reaction, right? In doing that, we then create the other cyclic part of the product that we're aiming at. Last thing to do is just regain the aromaticity that we temporarily disrupted by using the conjugate base of the acid we used earlier, which means that not only did we regain the catalytic acid, more importantly, we got the problem right, which is also good. Okay, gang, that does it for a bit of a bear of a worksheet. I hope you feel better about these reactions, but if you want to challenge yourself, I have a second worksheet where it's the same reactions, but I'm making them hard as heck on purpose. Anyways, thank you for watching this video. If you're watching this video, that means you've supported jOeCHEM financially, and I truly just want to say thank you. I hope this website is everything you are looking for, and it's propelling you to organic success. And I'm so glad you're using it now. I hope you're using it towards the end of your organic days, taking the class. And I hope to see you all in the next video.